Forward error, find the difference between the two vectors, and get the magnitude. Find the difference between the two vectors and get the magnitude. They're too far from each other, as you can see here. Try to find the difference between them. It's going to be too big. The error is not. It is a forward error, by the way, in this case. It's a very big error. Have a question? All right.
Doctor.
The backward error, if you try to plug in, B is given, A is given, XA is given here, the approximate solution, what is it? That's XA. That's XA. Try to calculate the residual and get the magnitude of the residual at the end. It is going to be quite small number, which tells us that the backward error is not something that you can rely on to measure how small or how big is the error. It's always better to calculate the forward error rather than the backward error. And for such a system, we find something that's called the condition number, like that will tell you in advance how good or how bad the matrix that you are trying to deal with. I mean, the matrix that we just had in the past example is one of the bad matrices where something that's called the condition number is not a reasonably small number. We're going to expect, like, I mean, given a nice matrix, the condition number of this matrix is supposed to be small. And if it is big, then trying any numerical solution might not give you a good answer. We'll see that in just practice in just a few minutes, by the way. Again, like every time you try to solve a linear system, I mean, Gauss elimination method, the one that we used to all the time. Well, it is very sensitive to the rounding errors, by the way, whenever the matrix is L conditioned. Again, we calculated something that is called the condition number. Matrix is basically K equal the magnitude of A times the magnitude of A underscore. That's the magnitude of A times the magnitude of A underscore. And if this, it is normally a number that is larger than 1. It is normally larger than 1. But if it is far larger than 1, then that's going to make your matrix is just an L condition. So يا جماعة
دكتور معلش يا دكتور انا مش عارفه امسكه طول المحاضره كده يعني امسك التليفون طول المحاضره.
سامع؟
مش هينفع امسك التليفون طول المحاضره. عايزين نحطه في مكان.
You may want to fix it in somewhere or another. You may ما اعرفش. عايزة تثبتيه بأي شكل؟
او ممكن اصور لإياد البورد.
مش ممكن. هو wants the lecture as well. It's difficult. You understand it? That's fine.
هو كمان في حد اتصل تقريبا فالفيديو وقف.
Right, guys. Again, this is called the condition number. It is normal a number that is larger than 1. Whenever it is far larger than 1, we call the matrix an L condition matrix, not a nice matrix, a bad matrix, by the way. If K here far larger than 1, A is small. And L condition matrix, by the way. لو سمحتوا الصوت لو سمحتوا صوت. Alright? Again, you would have a bad matrix whenever the number is too big. And actually, like suppose like your kappa or the K here is like as an example. Suppose your K here is, let's say, 10 to the minus 10 to the 6, for instance. A big number here, like 10 to the 9, whatever. And suppose you're running some approximate way to solve your system by either Gauss elimination. You're always going to have rounding, by the way. And the final answer that you're going to expect would have like a considerably large error that will take from the double precision. What is the double precision? It's just 16 digits. 16 digits. I mean, the 6 digit will be cut from the 16 digits. You're not going to expect an accuracy more than 10 digits here. you're not going to get an accuracy. The answer that you're going to end up having a solution minus an approximate solution that you calculated, that will be, it is not going to be, it is basically something like a 10 to the minus, to the 16, minus the order of omega there, that's going to be 6. So that's eventually going to be 10 to the 10. Of course, that's going to be in terms of minus, of course. That will be minus to the 10. So, wait a second. We have this 16 digits. We expect the accuracy will go all the way to 16 digits. But with the Gauss elimination, you're not going to expect more than the number of digits that comes after you cut off these 6 digits up front. We're going to see that just immediately in a couple of examples. And here they calculated how we define an elimination error. It's a formula that relates the error in the output related to the error in the input. Again, suppose you have a system AX equal B, right? And suppose the input here are what? Like this is the system that you want to solve. What are the inputs? What kind of inputs do we have for this system? A and B. A and B. A and B would be the inputs. The inputs here would be the end. Are the inputs. All right? What is the output? What is the output here? Solution. We want a solution. At the end, we want a solution for this system. You call this solution, well, it's not going to be the exact solution, but then end up having a solution that's A by 1. So giving me a system, I can give you like an answer after I plug it into the computer. Well, the formula that we have here, it gives you it relates the error that comes in the output compared to the error that comes in the input. We're assuming that when we have a small error in the input, we're not going to expect to have a big error in the output. But this is not going to be always the case for bad measure C is the one that we just had. Eventually, this number could be like a number that's quite big. Eventually, this is going to be like bounded by, the magnification factor is basically going to be always the magnification factor here of this ratio. Can be simplified. Eventually, I know it will be less than an A times AM. It's the condition number that we have. That condition number that we have. So, and this is going to tell you like how reasonable is the error in the data that you got, by the way. How reasonable? Just calculate this number, and that's going to tell you how reasonable is the error that you got there. Still, this is the theory so far. Here's a very important example. It's very well known in literature of mathematics. It's called the Hilbert matrix. It's called the Hilbert matrix. And it's very well known matrix to be like an L-condition matrix, where like anytime you solve like a bigger system with an Hilbert matrix, you're not going to expect much from the computer, by the way. Hilbert matrix. Matrix where the Aij squared is equal to 1 over I plus j minus 1. For any element that sits in the matrix, the element itself is going to be an I 1 over I plus j minus 1. Let me give you some, like an example here. Suppose I want to talk about the Hilbert matrix of order 3. That's going to be a 3 by 3 matrix, by the way. It's going to be a 3 by 3 matrix. Of course, this is going to be like an n by n matrix, of course. Definition, it's just going to be the same for any one of them. What is A11 here? 1. What is A12? A12. 1/2? Good job. Can go 1/2. 1 3. A third. It is symmetric matrix. It is symmetric matrix. It is a symmetric matrix. Okay. For the A22.
عشان الاديشن commutative.
Exactly. And what do we have here? A third. A fourth, a fifth. This is the case of the Hilbert matrix of the size 3 by 3. You can have it of any size you want. All what you need to do is just, like for instance, you need of degree n or degree 10, for instance, go all the way to 10 and down all the way to 10. It's a very well known matrix to be, to be like an algorithm. We're going to see that in just a few minutes. You take a question. Yes. Again, it's a very well-known matrix that it can show up, by the way, in an area where you have, let me remember, least square method. Least square method, I don't know if you heard about the least square. If you haven't heard about it, you'll see it later, by the way, in chapter 4. It's a matrix that comes from like an application, very well-known application. Given a set of data, finding a polynomial that will go through this data, by the way, or person will go through now. This is where it comes from, right? Very well-known matrix, but it behaves very badly. It's one of the examples where it behaves very badly. Yes.
How can it do بطريقة ثانية؟ Denominator 1, 2, 3, 2, 3, 4, 3, 4.
Actually, this is just like a quick way of writing it down. Okay, let's take a look at the calculation that we have here, by the way. They consider the case n equals 6. That's a matrix of the size 6 by 6. A Hilbert matrix of the size 6 by 6. It is built in the MATLAB. It's built in the MATLAB. And they're trying to calculate the condition number of the matrix, the Hilbert matrix that we find at the top, in terms of the infinite node. In terms of the infinite node, yes. What is it? Actually, that's the definition of any element inside the matrix. Like if you try to get any element inside, I suppose I'm talking about the matrix of the size 10 by 10. What is A9 here? What is it? It is 1 over 8 plus 9 minus 1. Whatever. This will define you any element inside this matrix. Like, the matrix is well defined by just this formula in there. So you can fill it in by just following. By the way, like every time you move from an element to another element, you have just to add a 1 to the denominator. Just need to add a 1. Like you could see it like 1, 1/2, 1/3, 1/4, 1/5, all the way down. So every time you move from the right to the right, you just add 1 to the denominator. Okay? Let's focus here on the calculations. What is the condition number of this matrix? You see it? The condition number of this Hilbert matrix is a number times 10 to the 7. Bigger than a million. A number that is bigger than a million. How many digits are we expecting to lose when you calculate, when you apply, for instance, Gauss elimination when solving such a system? How many, like what is the accuracy we're losing, by the way, when we have such a matrix, by the way? 16 minus 7. 16 minus 7. Well, they consider a system here, normally this is like a trick most of the statisticians are dealing with. Start with a system that has a solution that you know. We can have our matrix here of the size 6, multiply times a column of 1, 1, 1, 1, 1, 6 times, by the way. 1, 2, 3, 4, 5, 6. Alright? And calculate your answer and multiply. That's going to give you like some answer right hand side. Whatever that answer is, call this D. So I start with a solution that I know exactly. It is all ones. It is all ones. And how do I get my matrix here on the right hand side of column D? Multiply the matrix times a column of ones, and that's going to give me the D on the right hand side. All right. And now use the well-known command in MATLAB to solve such a system. How would I solve the system AX equal B in MATLAB? Exactly, A forward slash B, exactly, that's what we get. So if you solve this on MATLAB, it is going to be X equal A forward slash B. That's the way we can get it. Well, what is going on inside the machine to get you the solution? It's a very advanced method that would have an LU factorization. It's a very advanced method. We're not going to go like, and dig like what is that method is. But it is certainly the best known method to solve a linear system. It is the best known method, I mean, for MATLAB to solve the linear system, by the way. So we're going to go here. I have my B, and I have my H, and I will assume my X is not known, by the way. Let me assume my X is not known. I know the exact solution, and for like few minutes, I'm going to assume that the solution is not known. And I'm going to come up with the approximate solution that comes from the H6 backslash B. Here I'm telling the computer, please solve me the system that has the matrix with the size 6 by 6, where the B is given, the B is known there. And the exact solution is known. When you try this with the machine, that's the answer that you can get here, by the way. The solution that you can get is just right here. These are 3 components of it, by the way. These are 3 components. There are other 3 components on the other side. Could you look at how many digits are you losing, by the way, from this phenomena of a high condition number? How many digits are we losing here? 2? Is it right? I mean, they're supposed to be all 9s. Or 1. I should get the answer as 1 or all 9s, by the way, 0.9999. There should be that, by the way. But what is happening here, we're still losing some of the digits, by the way, in the solution. So this is an error. I mean, how many digits are we losing here? 4. How many digits are we losing here? 5. If we go down more. So on, so forth. Last one, 1, 2, 3, 4, 5. So we're having like you're not going to expect an error. I mean, that will cover all the 16 digits. You're going to lose some of the digits, by the way, because of the big condition number of the matrix. So do not rely much on the machine to give you a precise solution. The machine will not give you a precise solution if you have a bad matrix, by the way. Let's increase the size of the matrix into 10. The n equal a 10, and we're going to take a bigger Hilbert matrix. We're going to take a bigger Hilbert matrix. How big is the condition number? 10 to the 13. It's a huge number, 10 to the 13. It's a very huge number. Well, what are we going to expect if we ask the system to solve one of these problems that we just mentioned? Well, look at what is happening here. You only recover few of the 16 digits, by the way. I mean, while all the components should be 1s right here, well, could you see how big is the error? All of these are digits with error, by the way. All of these are digits with error. Where is this coming from? What is it?
It's more error than rest.
Exactly. I mean, where is this coming from? It is because the matrix is not nice. The matrix is coming with a very bad condition number. And this is answering the question, why do we use this course? Just punch a problem in the computer and get the answer. Like, do you know what kind of trash sometimes will you get from the computer if you have a bad problem? This is the rule of a numerical analyst, by the way. It is not every time you have a problem, you're just gonna punch it in the computer and you're gonna end up having a reliable answer. I mean, computer will not gonna be reliable. As long as you have good matrices, yes, you can rely on that. But for these type systems, you're not gonna end up having a good answer. Any question? Question here? I already mentioned this last time. We talked about the matrix norm and the vector norm. I want to take this work one more time. That's to prove that the magnification factor is not going to exceed the prediction number. It's not going to exceed the amount. Here is another source of error. Here is another source of error. So they can a very simple problem of the size 2 by 2. Very simple. Alright? We're gonna solve it in 3 different ways. Alright? One of them will be an exact solution. An exact solution we're not gonna approximate. We're not gonna approximate. The other one will be a way, we're gonna approximate while what we're solving using the highest accuracy that existed in MATLAB or any hand calculator, by the way. We're gonna approximate using the best technology we have, either the calculator or the MATLAB, and get an answer, and then solve solve it one more time after row swapping and see what was the difference. One more time. We're going to solve it 3 different ways. Find the exact solution. Find approximate solution by using the best technology. Swap the rows and repeat. Step 2, by the way, where you solve numerically with some approximation. So here how we resolve it. Can you check if Gauss elimination, anybody is having a problem with Gauss elimination? One more time, how would it go? You could look at the first entry there, it's almost a 0. It is a 10 to the minus 20, which is almost a 0. By the way, if you just ignore this element, it's not going to cause too much harm, but you're not going to end up having the exact solution. So let's keep this element and try to follow with the solution of the system. Gauss elimination is going on here, and get an element to this corner, and then go back and try to cancel that element on top. Eventually, this is the solution of the system. Shh, guys in the back, please, Basma. Here's the exact solution of the system. These 2 components. Well, we didn't approximate anything. We didn't use any calculator. We just kept the calculations accurate, by the way, without missing any number there. So this is what we're going to end up having. And can you approximate these 2 answers? Look at the numbers that are multiplied there, 10 to the 20, 10 to the 20 there. Well, this will be quite small, by the way, in front of like near to 10 to the 20. Guys, stop talking, please. هنبدأ نطلع ناس برا, by the way. هنبدأ نطلع ناس برا. You're going to feel well with that. Alright, so if you drop this number here, that's eventually going to give you roughly a 2 for the first component. Same, if you drop the 2 and 4 from the solution, you end up having 1 for the second component. Again, just drop the 4 and 2, so you're going to have a minus 10 to the 20 over minus 10 to the 20. That's 1. Alright, so this is the exact solution. When you approximate it, you just get 2 and 1 as a solution. Exact solution is being written here. The exact solution is being written. Well, let's use the best known technology, either the calculator or the MATLAB while solving. اللي هيحصل أنا going to multiply the top row times a negative 10 to the 20 and add it to the second row. Okay, so what is that going to give me? Well, that's going to give me 0 here. So here 10 to the 20 times the negative sign added to the 2. It's going to give me this number. Whatever, and then 10 to the 20 times this number times the negative sign added to 4. It's going to give me this number. Agree with that? Question so far? Any question? Well, how is the approximation in MATLAB going to go? Can somebody tell me how is the approximation in MATLAB going to go? I mean, all the calculations done here are exact. Well, I mean, the number 2 and 4 will disappear. Why? It is near a huge number, 10 to the 20. It can be ignored there. It will be exactly ignored. Either you work in MATLAB with a high precision, by the way, which is 10 to the 16, or with the hand calculator. It will never keep this number, by the way. Wait a second. This is what we did here. I mean, when you drop the 2 and 4, it's like you killed the second row. The second row has been killed, by the way. It's as if it was not there. It was just zeros up there, by the way. And this is the phenomena that will, I mean, they give you a solution that is not going to be acceptable. Let's go and see what is going to happen next. Well, the x2 value is easy to get. The x2 value will be 1, very close to the one that we just had a minute ago, very close to the exact solution. However, we try to look at the x1 solution, it is 0. While it was 2, by the way, up there. It was 2. It is 0 here and 2 up there. Well, this phenomena is called the swamping because I mean the factor that you multiply with it's a huge factor, and when we add the 2 rows like together, you deleted the second row. I mean, second row as if it was not there. It was just zeros up there. This is called swamping. It is just deleting one of the rows, and this error is coming exactly from this phenomenon. X1 is 0. It's because you just deleted the second row. Well, how to get rid of this phenomenon? Try to keep the multiplicative constant you multiply with, the m's, if you remember the m's. Do you remember the m's? Try to keep them as small as possible, and it will be the best if you try to make them smaller than 1, by the way. It will be the best if you try to make them smaller than 1. Well, how to achieve that? This is the strategy that is called partial pivoting. Partial pivoting means the following. Compare these two elements in the first column, by the way. Which one is bigger? The 1 or the 10 to the minus 2, the 10 to the minus 20? 1 is bigger. Then I'm going to swap row 1 and row 2, by the way. I need the bigger, look at the column, look at the entire column where the pivot is, and find the element with the highest value. Suppose it is located in the 10th row, by the way. The element with the highest value. Of course, I'm going to take the absolute value for all of them. So if it has the highest absolute value, it will be coming instead of it will be swapped with the first row there. Swap, yes, you have to swap. You have to swap.
You don't have to sort backward?
No, just, to look at the element that comes with the biggest absolute value in the body. We're at the location, let's say A11. Look below, and suppose you have, let's say the biggest element there is -7. With the absolute value, of course. This is located in row number 10. This is located in row number 1. I'm going to swap row 1 and row number 10. I'm going to swap row 1 and row number 10. That's exactly the strategy we're going to follow here in the third solution. All right? So we swap row 1 and row 2. And then go ahead with your calculations. I need to get rid of the number that says down here, multiply times 10 to the minus 20, which is quite a reasonable number now. It's not going to be 10 to the 20 anymore. It's going to be 10 to the minus 20. It's a very small number. And add it to the second row. There is no approximation so far. When you approximate what happened here, suppose you're working with MATLAB or a calculator, what is the approximation of this and that would be? 1, is that right? You're going to cross off the 10 to the minus 20 terms. You're going to cross off the 10 to the minus 20 terms. Well, we kept the second row. We kept the second row. All the changes that comes from the top row, it just hasn't been altered the first row. So we kept the second row there. So if you drop these, you're going to end up having 1 times y equal 1. That's going to give you the value of y, which is 1. Go backward, and that's going to give you the value of x that will be close to the I think it will be 2. No, the same. It will be just very, very, very close to the first answer we got. The exact answer that we got there, be very close to it, by the way. And this is now to us a new strategy that, and that's what we call the partial pivoting. Anytime you want to apply Gauss elimination, make sure the constant that you multiply with is not too big constant. And the best strategy, just take this constant to be absolutely less than 1. And in that case, you always need a row swap while you're carrying out Gauss elimination. This will take us now to partial pivoting, and that's how it goes. Let's go with this system. How to solve it with partial pivoting. It is not the regular Gauss elimination, please. It is not the regular Gauss elimination. It has a strategy so that all the constants you multiply with would have a size absolutely less than 1. Would be all, the multiplicative constant you multiply with, in order to carry out the Gauss elimination should be, like less than 1. The first step here, what should happen? Look at the first element of the top corner, 1. And the column below. Which element would have the highest value in terms of the magnitude? Take a look at the first column here. 2 is the biggest. Is that right? 2 is the biggest there. So I'm going to go and replace or swap the first and the third row. That's because I need the biggest element to sit at this pivot there. I need the big, even if it has a negative number. That's again, take the absolute values and take the biggest number among all of these. And then go ahead and do calculations. What is the m here? Where is the step? It's right here. swap row 1 and row 3. What is your m that you're going to multiply the second row times or the first row times and then add it to the second or the third? Let's try to find out the m's. Where's m1? Remember, like the constant, we multiply the first row times and then change the sign and add it to the second row, for instance. What is it? It is, if you remember, it is a12 divided by a22, a11, I'm sorry. In this case, it's going to be -1 divided by 2. Yeah, absolutely less than 1 here. It has an absolute value less than 1. You multiply this number times your top row, and insert an extra negative sign and add. This will give you the matrix that will come in the second one here. All right? Repeat the work one more time. How they get rid of the 1? Same. Multiply the 2 times whatever times -1/2 and add it to the third row to get a 0 in this location. Any questions so far? It is not Gauss elimination. It is something, I mean, while you're calculating, keep in mind the element that should sit in the diagonal should have the highest absolute value compared to the rest of the elements sitting in the column below. JJ, by the way, should be the absolute value of it. It's going to be the biggest compared to the absolute value of the rest of the element in the same column that comes below. Well, here, we're coming to a smaller matrix here. What will happen? Yes, we need to swap row 2 and 1. I mean, we're working with the pivoting strategy here. We're working with the pivoting strategy. The -2 should go up. I mean, the second and third row should be swapped. And then multiply this row times whatever to get rid of the row that goes below, and that's eventually going to give you this matrix. And this strategy, by the way, well, it is not going to expose your solution to the swamping phenomena. Like the example we had a minute ago. The number that you're going to multiply with, they're going to be like reasonably small, and it is not going to. I mean, again, it's not going to give you like a nonsense answer again. So this is called partial pivoting. There is a method that's called total pivoting. We're not going to consider it here in the class. You may want to find it in the textbook of Bertrand Affairs if you want to read it. But we're not going to go over the total pivot. So eventually you get to the solution of the system. Of course, everything is being done exactly here. There is no explanation. Question? Any question here so far? Question? All right. Well, we said while we're working with the partial pivoting, we need to permute rows, by the way. We need to permute rows. And if you remember, one of the tasks that we had before was solving the system by the LU factorization. I mean, suppose you have like these 2 many systems where you need to, solve like 2 many systems where the matrix is the same. So we have to factor the matrix and then apply the LU factorization to every system that comes in. In the case that we're talking about here with the permutation, this pattern is not going to be right, by the way, because I mean, it is not only an L and U that will be showing up in your calculation. There is a third matrix that will be called a permutation matrix, and in that regard, you're going to end up having this pattern, by the way. P is just a permutation matrix. We'll define it in just a few minutes. Permutation matrix times our matrix A will be factored into the LU, by the way. And a small alteration to the earlier one that will include the row swapping in the calculation, by the way. That will include the row swapping in the calculations. First of all, what is the permutation matrix? Well, I mean, for the 2 by 2 matrix, like what are the different matrices that we can get from the identity matrix there? I mean, here's the identity matrix of the 2 by 2 size. Well, if we swap the first row and second row, what do we get? 0, 1, 0, 1, 0. You with me? Is there any other permutation matrix there? Is there any other permutation that we can apply on these types of matrix? The identity matrix of the size 2 by 2. There is no other permutation matrix, okay? So how about the 3 by 3 matrix there? The 3 by 3 identity matrix. How many permutation matrices are expected there?
N for N by N.
N factorial. Will be always N factorial. So whenever the size 3 would be as 3 factorial, that's going to be 6. Like how many ways you shuffle 3 numbers? I mean, it's N factorial all the time. So here, the way you can compute the rows of this matrix are 6 different ways. The identity matrix itself, and all the permutation that comes after that, by the way. All the permutation that comes after that. Fundamental matrix of fundamental theorem of permutation matrices. What does it say? What does it say? Let me be an n by n permutation matrix formed by particular set of row exchanges. Let's say like I'm going to swap row 5 with row 7. I'm going to swap row 8 with row 9. All right?
هو فين الثيرم في الجملة؟
Let's read it. P is just a sort of permutation matrix that's been done by a set of row swapping, by a finite set of row swapping. Let's say R1 swap with R5, R7 swap with R whatever.
يعني لو ضربنا في P في أي كمان
If you multiply the P from the left by P, you're going to get the same effect on A, by the way.
يعني لو ضربنا
Take the matrix for instance. 0, 0, 1. 1, 0, 0. 0, 1, 0. What kind of permutations do we have there? What kind of permutations?
third row, first row, second row.
Let's see the permutation that we have there. I mean, we're trying to compare this to the identity matrix, by the way. We're trying to compare this to the identity matrix. I will get my original matrix. Suppose my identity matrix is just.
هو مش هو ده اصلا تعريف المالتيبليكيشن باي رو فيكتور؟
What is it?
مش هو ده التعريف بتاع المالتيبليكيشن باي رو فيكتور؟ لما بنطلع باي رو فيكتور على الشمال ناخد يعني ده بيسلكت
Yeah, we'll pick one element from there exactly. That's what is going to happen. So I mean the same sort of operation that is being applied on the identity matrix will be the same if you multiply P from the left hand space. Did you get what I mean here? It's not quite clear, by the way. So let's try to get what kind of operations are made here in order to get this matrix here. What kind of operations? What kind of operations? Well, what happens here? I have to swap row 1 and row 3. Is that right? Row 1 and row 3. What else? We'll give you 0, 0, 1, 1, 0, 0. Second row is not going to change. I still need one more operation.
2 and 3.
Swap 2 and 3. Swap 2 and 3. So again, I got P from the identity matrix by these two operations. Multiplying P times A will have the same set of operations on the A itself.
How do you predict ahead of time that you will need further exchange? يعني ما انا ممكن وانا بعمل الاليمينيشن يظهر لي زيرو في حته انا مش عايزها. عايز بقى اعمل سواب. ازاي اعرف قبل ما ابدا اعمل انيو فاكتورايزيشن ان الزيرو دي مش هتظهر؟ ازاي اختار البي قبل ما اعمل انيو فاكتورايزيشن؟ ازاي اختار البي؟
Oh no, the P will be constructed while you're working. You cannot know the P in advance. You're gonna construct the P while you're working. P is not gonna be known in advance.
طب ما هو كده في المالتيبليكيشن على الشمال هيبقى في ايز
If P على فكرة eventually, by the way, we'll take that into account in the calculations. By the way, we'll take that into account in the calculations. Right? So this is exactly what is happening here. Again, the same set of operation when applied on the P matrix will produce, the The same kind of permutation of the matrix A will multiply the A from left by the T. Right? And another thing that you want to know about this matrix, what is the average of T? Somebody, I guess?
العكس بتاع اللي احنا عملناه بقى.
What is the average?
مش عارف.
It is you may want to spend some few minutes at home. I don't. It is a B transpose. The inverse of any permutation matrix here, by the way, it's always the transpose of the matrix. It is always the transpose of the matrix. You may want to go home and try to see like why this is the case, at least for the 3x3 cases. All right.
نعم.
Is that too much time?
مستنى.
أنا وقت كتير؟
هي المفروض وربع فاضل 5 دقايق.
5 دقايق 5 more minutes.
خلاص افرج الراجل عامل شكل كده مش فاكر
All right, guys. Any questions? Any questions? All right, we're going to start taking